Welcome to our presentation on industrial maintenance and reliability. Today, we are moving beyond maintenance as a series of reactive repairs and looking at it as a practical operating system. Whether you are an engineer, manager, or technician, this framework provides the strategy and tools needed to transform technical work into business value through precision, monitoring, and discipline management. The foundation of any high-performing technical team is a shared mission. Reliability isn't just a maintenance goal. It's the bridge that connects safe work practices to dependable production capacity. When operations, engineering, and supply work together, they protect the functions the business needs most, ensuring that performance is safe, stable, and sustainable over the long term. It's important to remember that reliability is a business outcome, not just a metric for the maintenance department. At its core, reliability is about delivering a required function under specific conditions for the required time. By focusing on preserving function rather than just fixing machines, we directly impact safety, throughput, quality, and the overall lifecycle cost of business. To work effectively together, we must use a common language. This table provides our working definitions for key terms like asset, reliability, and maintainability. By aligning on these definitions, we can ask better management questions. For instance, instead of asking, when can we fix it? We should be asking which action manages the failure risk most economically. Sustainable performance emerges from a balanced system. While technology like sensors and analytics can amplify our results, it cannot replace the fundamental pillars of people, process, and data. We need competent leadership, standardized work processes, and an accurate asset hierarchy for technology to truly create value. Asset management is the link between high-level enterprise objectives and our daily technical tasks. It takes those broad goals, like safety and capacity, and translates them into specific strategies and work management steps. This creates a learning system where every failure provides data that helps us refine our strategy and improve future capital projects. To make reliable decisions, we need a stable foundation of data. This begins with a clear asset hierarchy. From the facility level down to specific failure modes, we must maintain unique identities, bills of materials, and consistent coding. Remember, your CMMS is the system of record, but it's the quality of the data we put into it that defines our success. Now let's look at strategy. A good maintenance strategy must actually change the technical decisions we make in the field. By understanding criticality and operating context, we ensure that our most rigorous efforts are directed where they create the most value for the business. Criticality is the tool we use to prioritize our resources. It's not the same as work order priority. Rather, it's a classification based on safety, production impact, and repair costs. A class asset deserves higher rigor in maintenance strategy, condition monitoring, and spare parts availability compared to a lower class asset. Choosing the right maintenance strategy depends on how an asset fails and what happens when it does. We move from condition-based tasks, where we detect degradation early, to time-based tasks for age-related failures, or even run-to-failure for low-consequence items. The key is that every task interval must be backed by evidence and engineering analysis. Reliability-centered maintenance, or RCM, provides 7 discipline questions that guide our choices. It's a decision process, not just a fancy name for preventive maintenance. By systematically identifying functions, failure modes, and consequences, we ensure that every proactive task we assign is both applicable and effective. It's much easier to maintain reliability if it's built in from the start. This means we must address maintenance during the design, procurement, and commissioning phases. Capital projects should hand over verified performance and maintainability data, not just a pile of equipment, ensuring we can operate within a sustainable envelope from day one. Moving to our next section, preventing defects. The goal here is to stop issues before they even become failure modes. Precision maintenance is the key, turning engineering requirements into repeatable field standards and verified as-left conditions. Precision maintenance is about controlled installation and assembly. It requires sticking to technical standards for things like torque, alignment, and lubrication. We also emphasize quality assurance through hold points, where work is verified against acceptance criteria before moving to the next step, ensuring every job is done right the first time. A simple but powerful tool is Clean to Inspect. When we clean a machine to a specific standard, we aren't just making it look good. We are creating an opportunity to expose developing defects like leaks, cracks, or overheating. Every abnormality we find during cleaning should be converted into controlled work before it leads to a failure. Precision lubrication is critical because it controls friction, wear, and heat. It's not just about adding grease. It's about getting the right lubricant to the right point in the right quantity at the right time. We must verify delivery and avoid common mistakes like overgreasing or using contaminated transfer containers. Contamination control must protect the lubricant from the moment it arrives at our site until it's inside the machine. This means using sealed storage, dedicated clean transfer tools, and high-quality breathers. We set cleanliness targets based on the sensitivity of the components, using oil analysis to verify we are meeting those standards. Proper alignment starts long before you mount the laser. We have to ensure the foundation is solid, correct any soft foot issues, and account for thermal growth. By following approved tolerances and recording both as found and as left results, we significantly extend the life of bearings, seals, and couplings. Balancing the rotor assembly is another precision requirement. We calculate permissible residual unbalance based on the rotor's mass and speed. It's important to note that balance quality at the shop and final machine vibration in the field are different measurements. We need evidence that both meet our acceptance criteria. Reliability is also an operational discipline. Operators protect the process by keeping equipment within its designed operating envelope. This includes following precise startup and shutdown procedures, performing basic care inspections, and managing controlled changes to raw materials or recipes that could stress the equipment. Even with precision maintenance, degradation will eventually occur. Our third focus is detecting that degradation early enough to act. Condition monitoring only provides value when a finding is turned into a planned, risk-ranked work order that is executed before a functional failure happens. This brings us to the P-F interval, the time between when a potential failure is first detectable and when the asset actually fails. Our entire workflow, detecting, diagnosing, planning, and scheduling, must fit within this window with enough margin to act safely and effectively. We should layer our inspections to catch defects as early as possible. This starts with automated protection systems, followed by specialist analysis like vibration or infrared. However, maintenance craft observations and operator basic care are just as vital, as they are closest to the assets every day. Choosing the right technology is about matching it to the failure mode. Vibration is great for rotating equipment, while infrared is essential for electrical systems. The key is understanding the engineering caveats, like sensor location or emissivity, to ensure the data we collect is accurate and repeatable. When an alarm goes off, it's the start of a decision, not the end of the process. We need strong alarm governance to validate the data, diagnose the cause, and rank the risk before creating a work order. We measure our success by how quickly we move from an alert to a reviewed finding and, ultimately, to a completed repair. To close the loop on a condition finding, we must document everything from the initial evidence to the post-maintenance test. We need to confirm that the as-found condition matched our diagnosis, and that the as-left measurements show the asset has returned to its healthy, expected state. Now we move to work management, which is the engine of our reliability system. This disciplined flow converts risk and technical data into work that is safe, ready, and executable. Without this engine, even the best strategies and monitoring won't lead to improved performance. We use a visible work lifecycle to track every task from request to closure. Every step needs a clear owner and exit criteria. It's vital that waiting is treated as a controlled status in our backlog, not a black hole where work disappears and is forgotten. A high-quality work request is the start of a successful job. It should describe the problem, what changed, and what the evidence is, rather than just guessing a solution like replace the bearing. This allows the planning team to investigate the root cause and prepare the correct scope of work. Priority is a combination of consequence and time criticality. We use a matrix to decide how fast we need to act. AP1 is a true emergency that requires immediate response, while AP3 is a planned job where the risk is controlled and we can set a due date based on the evidence we've gathered. It's helpful to distinguish between planning and scheduling. Planning is about what and how, preparing the scope, safety permits, and parts. Scheduling is about when and who, committing our labor capacity to work that is actually ready to be done. We schedule people to ready work, not just whoever happens to be free. A complete job plan removes uncertainty for the technician. It includes everything from hazard controls to technical specifications and torque values. A good plan is a reusable asset. We should use feedback from the field to improve it every time the job is performed, rather than relying on memory. Only ready work should make it onto the frozen schedule. This means all materials are on-site and all constraints are cleared. We must also manage our backlog health, ensuring we aren't overloaded and that we are addressing work based on risk and due date, not just volume. Once a weekly schedule is frozen, we must protect it. Every break-in, unplanned work that disrupts the schedule, must be governed and classified. Break-ins are data points that tell us about our system's health, whether it's a genuine emergency or a failure in our planning process. Execution isn't finished until we return technical evidence. We need to capture as-found conditions and dimensions, prove the function with a test, and provide feedback to improve the job plan or bill of materials. This ensures that every job contributes to our collective learning. For shutdowns and outages, we need a gated readiness process. We don't want to be accelerating work at the last minute. By defining, challenging, and freezing the scope early, and ensuring materials are physically staged, we can execute the critical path safely and stay on schedule. Materials reliability is another key part of the engine. A reliable storeroom ensures the right parts are available and preserved in good condition. We use data to link parts to specific assets and maintain a reparable spare loop, treating inventory accuracy as an engineering control rather than just a warehouse metric. Our fifth pillar is defect elimination. We must learn from every failure and remove the conditions that cause them to repeat. The goal isn't just to write a report. It's to implement sustained controls that either prevent the failure entirely or significantly reduce its impact. We use structured root cause analysis, RCA, when the consequences or risks justify it. The first step is always to preserve evidence, like failed parts and process trends, before they are disturbed. We focus on the conditions and decisions that led to the event, using the simplest method possible to resolve the uncertainty. Defect elimination closes the loop. Once we analyze the causes, we must select and implement controls, which might mean changing a design, a precision standard, or an operating practice. Finally, we must verify that these changes actually worked and that the defect hasn't returned. To manage all of this, we need a balanced system of KPIs. We look at lagging indicators for outcomes like asset-related loss, leading indicators for our process health like schedule compliance, and technical indicators for quality like precision acceptance. Never publish a metric without a clear decision rule for how to act on it. We also need to understand the relationship between reliability, maintainability, and availability. Availability can be high even if reliability is poor, provided we are very fast at repairs. However, for a stable business, we aim for high reliability first, reducing the frequency of interventions. Role clarity is essential for good governance. We use a RACI matrix to ensure every decision, from asset strategy to weekly scheduling, has a clear owner and that the right people are consulted. While titles may vary, the accountability for these key decisions must be preserved. Transformation doesn't happen overnight. We build maturity in stages, starting with stabilizing our language and work visibility. Over time, we standardize our plans and precision, optimize through RCM, and eventually move toward predictive analytics and full lifecycle management. The key is to start with the fundamentals. In closing, reliability is the result of disciplined, technical work that is repeated and improved every day. By managing risk, using a common language, and building precision into everything we do, we create a system that is safe and sustainable. Let's focus on doing these fundamentals with rigor and making every cycle better than the last. Thank you.